Welcome back. Last class we started solving problem 7 and finished it, where we determined the shear stress and the drag force by the technique that was taught in the lecture itself. Now we are going to proceed to apply the von Karman momentum integral method for turbulent boundary layer over a flat plate. Okay, because that particular equation was valid both for laminar and turbulent fluid flow. Actually, Prandtl assumed 1/7 power law of velocity distribution for turbulent boundary layer. That was his assumption, and he said for turbulent boundary layer, small u by capital U is a function of eta, and eta is 1 to the power 1 by 7, where eta, the usual meaning is eta is equal to y by delta. Y is the distance above the plate and delta is the boundary layer thickness. All right. And since that von Karman momentum integral equation is applicable here too, it yields tau w is equal to 7 by 72 rho u square d delta by dx. Okay, if you follow the same procedure, this equation is more important. Okay. Now Blasius gave the following expression for wall shear for a hydrodynamically smooth surface. He said that tau w is equal to 2.28 into 10 to the power minus 2 rho u square into v by lambda delta u raised to the power 0.25. This is another equation. Okay. Now if we equate both, okay, this is the equation that we get, delta as a function of lambda delta and x, and if we integrate the above equation, we are going to get lambda to the power 0.5 delta delta to the power 0.25 d delta is equal to integration from 0 to x 0.235 nu by u raised to the power 0.25 dx, and then we can obtain expression like this, or if we multiply x here, right, and x here as well and take it out here, we can actually write this x becomes x to the power 1.25, okay, and this is Reynolds number. A similar expression. So simply what we have done is, so this was delta to the power 1.25, so this will become 0.25 divided by 1.25 when in writing in terms, 0.294 will become 0.376 x into Reynolds number to the power minus 0.2, and this is valid for Reynolds number 5 into 10 to the power 5 between 10 to the power 7. This is the boundary layer value for a turbulent flow. Now some observations. If you see, remember the laminar boundary layer was lambda x was a function of x to the power half. For a turbulent boundary layer is a function of x to the power 0.8. All right. So this means that the turbulent boundary layer grows faster. You see, as it grows as x to the power 0.8, and this grows at x to the power 0.5. There is a term called local coefficient of drag, CD star. So CD star is given by nothing, it is a ratio of tau w, the shear stress near the wall, divided by half rho u square. Average coefficient of drag CD is given by force drag divided by half rho a u square. So, this is the ratio of the shear stresses sort of, and this is the ratio of forces. Okay. So, now the analysis gives us that for Reynolds number between 5 into 10 to the power 5 and 10 to the power 7, this is what we got. Boundary layer thickness was 0.376 multiplied by x into multiplied by Reynolds number to the power minus 0.2, and CD gave us 0.072 into Re at L to the power 1 by 5. As if you put in those values, we can get CD as follows. Okay, where Re at length L, it's U capital L by nu, where L is the length of the plate. Okay, and for increasing, so if the Reynolds number is more than 10 to the power 7, Schlichting gave an empirical equation that gave CD as 0.455 divided by log to Reynolds number to the power 2.58. You do not need to memorize this equation. Okay. So, now using this analysis of turbulent boundary layer over a flat plate, what we are going to do is we are going to solve some problem. This actually is always a good method for understanding the complex problems of the boundary layer analysis in turbulent boundary layer. So, we start with the problem that says that the water flows over a flat plate at a free stream velocity of u 0.15 meters per second, that is capital U, right. There is no pressure gradient and the laminar boundary layer is 6 millimeters thick. Assume a sinusoidal velocity profile like this. Calculate the wall shear stress and the local coefficient of drag. So, we have to calculate the wall shear stress and local coefficient of drag. All right. So, how do we attack this problem? So, as always, we are going to have the things that are given. So, given capital U is 0.15 meters per second. Okay. Delta is 6 millimeters, or delta is 6 into 10 to the power minus 3 meters, for example, and U by capital U is sine of pi by 2 into y by delta. Okay, and mu here is given as 1.02 into 10 to the power minus 3 Newton second per meter square. So, now we do du by dy, for example, right, that gives us d dy of u comes this side, pi by 2 sine pi by 2 y by delta. Okay. So, this gives us u will come out cos pi by 2 y by delta into pi by 2 delta. All right. So, now du by dy at y is equal to 0 will be, we substitute y is equal to 0 here. So, this becomes pi capital U by 2 delta. If we put y is equal to 0, this cos term is going to be 1. Okay. And we know that tau naught is equal to mu du by dy at y is equal to 0. So, tau naught is going to be mu du by dy at y is equal to 0 again. So what we write is mu is 1.02 into 10 to the power minus 3 into, okay, I will write it on the next line, better to. So tau naught is going to be 1.02 into 10 to the power minus 3 into pi by 2 into u by delta, and after substituting in the value 1.023 into 10 to the power minus 3 into pi by 2 into u is 0.15 and delta is 6 into 10 to the power minus 3, tau naught comes to be 0.04 Newton per meter square. Very simple to solve, right? So local coefficient of drag CD star is given as tau naught by half rho capital U square, and simply putting in the value 0.04 divided by half into 1000 and u is 0.15 whole square, and this comes out to be 3.55 into 10 to the power minus 3, or CD star finally is 3.55 into 10 to the power minus 3. So one very simple question, how to be, I mean, just by using the definitions of CD and shear stress, the shear stress near the wall, we have found out this. So this was one problem. We will see another problem which says that air at standard conditions flows over a flat plate. The free stream velocity is 3 meters per second. Okay, find delta and tau w at x is equal to 1 meter from the leading edge. Assume a cubic velocity profile. For air, nu is equal to 1.5 into 10 to the power 5 meter square per second and rho is equal to 1.23 kilogram per meter cube. Okay. So what we are going to do, we are going to given u is equal to 3 meters per second, right, nu is equal to 1.5 into 10 to the power minus 5 meter square per second, and rho is given as 1.23 kilogram per meter cube. All right. So we have seen that cubic boundary layer profile is small u by capital U is equal to 3 by 2 from our laminar analysis minus half y by delta cube. Okay, for which boundary layer thickness is 4.64x under root RE of x. Okay, and tau w is 3 by 2 mu capital U by delta. So at x is equal to 1 meter, Reynolds number at x is going to be ux by nu. So 3 into 1 divided by 1.5 into 10 to the power minus 5, and this is going to be 2 into 10 to the power 5. So basically laminar, right? Now delta is going to be 4.64 into 1 divided by under root 2 into 10 to the power 5, and this gives us 0.0104 meter. This is the delta, and tau w will give us 3 by 2 nu into rho into u by delta. So this is going to be 3 by 2 into 1.5 into 10 to the power minus 5 into to 1000 no, nu is directly given, right? No, yeah. Into 1.23 into 3 divided by 0.0104. So this is the way tau w can be found out. Just do some multiplication. I'll write it again, 3 by 2 into 1.5 into 10 to the power minus 5 into 1000 into 1.23 into 3 divided by 0.0104. Okay. So this is some small problems that we are doing using the. So now this gives us another. We'll solve another problem. If we consider a laminar boundary layer on a flat plate with a velocity profile given by the cubic velocity profile, that is what we have seen. For this profile, we already know, determine the expression for local coefficient of drag. All right. So how to do that? Okay, so we know everything here before, so we will get directly to the point here. For given profile, we have already derived that tau naught is 3 by 2 times mu times u, sorry, I'll write it again. We have seen that tau naught is equal to 3 by 2 mu u by capital U by delta, okay, implies tau naught is equal to 3 by 2, mu will remain mu, capital U will remain capital 2, but delta is the equation we had derived, 4.64x under root RE of x. Okay. All right. So this is our tau naught, or if we just simplify it more, this 3 by 2 and 4.64, it will become 0.323 into mu capital U by x under root REx. Now what is the local coefficient of drag? Tau naught by half rho u square, correct? So CD star tau naught is 0.323. So basically this is sort of a derivation of steps which some results which I showed you directly. So now this is the derivation in terms of a question, okay, and I basically skipped it so that we could solve it as a question. So mu capital U by x under root REx divided by 0.5 rho capital U square, or CD star is equal to 0.323 capital U by x under root REX into 0.5 rho U square. So you can actually cut this U and U here one. So CD star can be written as 0.323 divided by 0.5 mu by rho capital UX under root REX. So CD star is equal to, this will be 0.646, and now this mu by rho is nu, and this is capital U under root REX, or 0.646, and this is Reynolds number. So CD star finally can be written as 0.646. Okay, I will take the eraser, write it properly. 0.646 divided by under root, so this is the drag coefficient, 0.646. all right. So this is the solution to one of the other questions. One more problem. So the velocity profile for laminar boundary layer is given by, so it's not a cubic but it is a one more term. Obtain an expression for boundary layer thickness, shear stress on plate, drag force on the plate, and the average drag coefficient. So this is a question where you have to find almost everything. all right. So you have to closely follow the procedure here. Okay, I'll try to lay down the procedure and write the results, but you are expected to solve this problem at your own, at your home. So we have been given, so problem number 11 is, we have been given U by capital U, small u by capital U is 2y by delta minus 2y by delta whole cube plus y by delta to the power 4. So first thing that we calculate the momentum thickness, because that is required in Van Korman momentum integral equation. So it's 0 to delta U by capital U into 1 minus U square by capital U square dy. Okay, so this profile you substitute in this equation. Okay, and after substituting you integrate in with respect to y vary from 0 to delta, and what you are going to obtain, I'll just write down, there are many terms. So one of the term, first term will be delta minus 4 delta by 3 minus delta by 2 plus 9 by 5 delta minus 2 delta by 3 minus 4 delta by 3 plus delta by 2 minus delta by 9. Okay, so the momentum thickness that you are going to get is 37 delta by 315. all right. Now this is the first step. Second, you have to use momentum integral equation. This is the first step. Secondly, what you do is, in any type of such type of equation, use momentum integral equation, and what do you do? Tau naught is rho u square d theta dx. Okay, and we substitute theta here from this one, and what you do is so tau naught can be written as rho u square into 37 by 315 d delta by dx. Okay, so this is tau naught. All right, this is equation number 1. Second is you use Newton's law of viscosity. Use Newton's law of, this is the standard way to solve all these stuff. If you follow this, everything is easy. Is equal to mu du by dy at y is equal to 0. Okay, so u velocity profile we already know from here, right? So this point, and we do this tau naught will be, so after differentiating what we get is 2 capital U by delta, okay, minus 2 capital U by delta cube into 3y square plus u by delta to the power 4 into 4y cube, and you substitute y is equal to 0, therefore you get tau naught is equal to 2 mu capital U by delta. This is number 2. Okay, so this is 1 and this is 2, and what is the best way? You equate equation number 1 and equation number 2. Okay, so we will go to another page. So after equating you get 2 mu u by delta is equal to rho capital U square into 37 divided by 315 d delta by dx, and if you integrate it, so it will become something like delta d delta with before integration 630 by 37 into mu dx by rho into u, or delta square by 2 is equal to 630 by 37 capital Ux by rho u plus c. Okay, the boundary condition here is that the boundary condition at the leading edge is going to be, the boundary layer is going to be 0, which gives c is equal to 0. Okay, so this is leading edge, this is the boundary condition. All right, so implies if you put here in terms of, because this is going to be Reynolds number, 1 by Reynolds number, right? So this is going to give you delta is equal to 5.84 x by under root REX. All right, so this is how you get delta. Now you can obtain 2 mu capital U by delta. So delta is known from here and everything else is known, so you can obtain tau naught as 0.34 mu capital U by x under root REX. All right, now the drag force is simply nothing but 0 to L tau naught b dx. Okay, and if you substitute it in terms of x, you are going to find out, I think you do this at home, Okay, you substitute all these values tau naught in terms of x. Okay, also you Reynolds number you put at u and x and everything, and then you can get 0.68 b mu capital U under root rho u l by capital U by mu. This actually is Reynolds number at L. Okay, but anyways, this is the thing. And lastly is the remaining is the drag coefficient, you know, CD is given by FD divided by half rho A capital U square. Alright, so FD, you know, everything is known. So okay, I'll just show in a little more detail. It is 0.68 b mu capital U under root rho u l by mu divided by half rho b is the area is b into length into u square, and this will give us 1.36 into 1 by rho u l by mu, or finally CD is 1.36 by under root RE into L, where RE Reynolds number at length L is rho u capital L by mu. So this is how you have seen for any velocity profile we are able to find out almost all the parameters that we know. Okay. So what we do is we will stop this lecture here and resume with a problem, and then in the next class, and then we will go to the final chapter of the boundary layer analysis. Okay, it might require 1 or 2 more lectures. Thank you so much.